It's like designing a full adder circuit making use of a 4:1 mux. We will be provided with a 4:1 mux in the sense input 0, input 1, input 2, input 3, and a single output, a 4:1 mux, 4:1 mux, 4 inputs and 1 output, and another 4:1. We will be need of two 4:1 muxes in this case. Another 4:1 mux with the input 0, input 1, input 2, input 3. Another 4:1 mux with single output, one for indicating the sum result, and another one for carry of the full adder. So like 4:1 mux will be having two selector lines. So here two selector lines common to reducing the circuit complexity. We have three inputs for a full adder. Here is our A. This A as input to first 4:1 mux and the second one also, and another like common input B input to both the muxes. Alright, and Cn, having that Cn over here, we need to provide, is that a Cn or the complement of Cn to I0, I1, I2, I3 to produce this sum for this combination of A, B, Cn, what that sum. So what should be the input to I0, I1, I2, I3, like that. In the same way, what should be the is that a Cn or a Cn bar to I0, I1, I2, I3 to produce this carry for these combinations of input. For that we need to have a tabular form like inputs, isn't it? I0, I1, very much similar to that K-map like thing, like no reductions but straight away answers, I2 and I3. On the other hand, we'll be having that Cn and its complement Cn bar. We'll have to have that Cn bar, and we need to find out for what values of zeros. 1, for what values of 0, 1, 2, 3, 4, 5, 6, 7. Cn is Cn and its complement. Check. Cn is 0 for 0. Cn is 0 for 0. Cn is 0 for 2. In the sense, Cn is 0 for 2. And Cn is 0 for 4. Cn is 0 for 4. That same Cn is 0 for 6 also. 6. And on the other hand, Cn is 1 for 1. Cn is 1 for 3. And the same Cn is 1 for 5. The same Cn is 1 for 7, and it's in the order like 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6 and 7. This is very much in the order. And designing for the sum part, what we have to check is, getting back to the truth table, we need to check for what values of 0, 1, 2, 3, 4, 5, 6, 7. The resultant sum is 1. We need to encircle that one. Once again, in order to design for the sum part, the upper part of the circuit, we need to go back to the truth table, and we need to encircle in this table what values of this table, for what values of sum, for what values of 0, 1, 2, 3, 4, 5, 6, 7, the sum is 1. The sum is 1 for 1. So encircle this one. The sum is 1 for 1. In the same way, the sum is 1 for 2. The sum is 1 for 2. The sum is 1 for 4 from the table. The sum is 1 for 4 from the table. And another one, the sum is 1 for 7. The sum is 1 for 7, and here comes the relationship between Cn and I0, Cn and I1, like that. So here for I0, Cn is encircled, so I0 input will be Cn straight away. And for I2, Cn bar is encircled, so I2 should be Cn, its complement Cn bar. I2 also, like Cn bar is encircled, so I2 input also will be Cn bar. And I3, Cn is encircled, so 7 is encircled in the sense I3 will be Cn, and making use of this one, we can go for I0, it's Cn straight away. We have that Cn over here, we have that Cn input over here. I0 is straight away Cn. I0 is Cn, and I1 is Cn bar, the complement of Cn. So plugging in NOT gate, which gives us the complement of Cn bar, and that is given over here. And I2 is also Cn bar. We have that Cn bar, so another connecting line from here, which giving Cn bar to I2. And I3 is straight away Cn. We already have that Cn at this point, so straight away to I3. This is for the sum part. And establishing for the carry part, the resultant carry. Once again the same thing, once again the same tabular form, like Cn bar, say Cn bar is 0 for 0, Cn bar is 0 for 2, so it's like 0, 1, 2, 3, 4, 5, 6 and 7. Now it's for the carry part. Now it's for the carry part, and getting back to the truth table and finding out for what values of guys, did I go wrong? No, it's 1, 1, yeah, correct. Yeah, for what values of 1, 2, 3, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, what values of 0 to 7 are 1 for the carry. Alright, so where do we have that 1? Do we have 1 over here, 1 over here? No. So no encirclement for 0, 1, 2 and 3. No, 3. It's 1. So we have to encircle 3. Here, carry is 1 for 3. Carry, we are evaluating for carry. Alright, we are evaluating for carry relationship. So carry is 1 for 3. So encircle that 3. And carry is 1 for 5. Carry is 1 for 5 also. And carry is 1 for 6 also. Carry is 1 for 6 also. And carry is 1 for 7 also. So there is a you might be like having a question in your mind. Nothing is encircled, so what should come? Both the values are encircled, so what comes over here? If nothing is encircled, remember, if nothing is encircled, it's a 0. In the sense, I0 to indicate the carry part, I0 should be straight away, it's a 0. We should have always a 0 input. And for I1, Cn is encircled, so it's a Cn. It's a Cn. I1, Cn is encircled, so it's a Cn. In the sense, I1, we already have a Cn. From that, another connecting wire over here, that's for I1. And I2, again it's Cn. Again it's Cn, I2. Same, extending the same connecting wire to I2, Cn, Cn is continuing all these part, Cn. And here both are encircled, so we have to go for 1. Remember, if nothing is encircled, it's 0. If both are encircled, it's a 1 value. And so we will have that always to indicate this one, 0 over here and 1 over here. That finishes the design for a full adder using 4:1 mux.